questions up to this point?
No, I don't think so.
Okay. Well, that's, a lot of it should be review. This will be some new stuff a little bit. So we ended with resonance structures. Can you see that?
Yeah.
Okay, so we start with these resonance structures. And the thing about these resonance structures is that you want them to be as, the more resonance structure, the greater the stability. Hey, there's a whiteboard over there. I'm going to use this whiteboard, all right? That'll work better. Not a big fan of chalkboards. Oh. Is that glare bad? Is that better? That looks better. All right.
That's good.
We got some resonance structures. And the more resonance structure the molecule has, the greater the stability that it will, the greater the stability of the molecule. All right. So ideally, you want as many resonance structures as possible. Okay. So we're just going to practice drawing some resonance structures. Remember, each one of these is going to be a carbon, all right? And bonded off of each one of those is going to be, in this case, it's going to be 2 hydrogen atoms, all right? However, with the exception of that, carbon's already got 4 bonds. And what we're going to do now is we're going to draw a resonance structure for this molecule. Even though it's a fairly stable molecule, what can happen is that one of these bonding pairs can come up to the oxygen. Now, the reason it would do that, you may say, well, why would it do it? Well, it's not very likely that's going to do it, but it can do it. And the reason it can do it is because oxygen has a greater electronegativity than carbon. So Mina and the rest of you that are listening, if you get your mind into thinking about this electronegativity, you get your mind thinking about that, then you've overcome quite a bit of organic chemistry. But you got to keep in the back of your mind electronegativity. It's a reoccurring theme through all of this. And so what happens is that if this bonding pair comes up to the oxygen, then what's going to form is going to be a single bond oxygen with 6 electrons. That's going to make the oxygen here negative and this carbon being positive. So far, so good? All right, so that's an example of one resonance structure. Another one we can do is we can look at a very similar molecule. But in this case, we now have a double bond over here. So there's going to be a double bond right here. What can happen is that this double bond, so if we were to number these, very simply as 1, 2, 3, 4, 5, and 6, we number them as such. What happens is we have a double bond between carbons 2 and 3. We can now rotate this up to there. All right, we can rotate that up to there. Now, what that's going to do is that it's going to cause this carbon to now have 5 bonds. Well, carbon can't have 5 bonds. It can't have 10 electrons in its valence shell. Therefore, one of these double bonds goes up to there, just what we saw in the previous example. Like that, and that's going to make this carbon atom here be a positive. That make sense?
Yeah.
Now, just to get your mind into thinking about this, because this gets to be a little bit tricky. So this hopefully makes some sense. Now, let's say that instead, let's say that we go back to the original molecule. Purple again. We have that. Now, could it go down there? Well, if we draw that out, if we draw that molecule out, we'll just redraw this again. So now we have that double bond here, but recall that there's also going to be two hydrogens there. All right. If we look at this now, if we look at this carbon right here, it's going to have 1, 2, 3, 4, 5. It has 5 bonds. It can't do this mechanism. It can't move that direction. The only reason this is not allowed because you have those 2 carbons. So when Dr. Baldwin has you do these resonance structures, you got to be conscious that he is leaving these places blank. But know, please, that there's going to be hydrogen atoms there. So you got to be careful. In order, if you're going to move a double bond, you got to have something which for another bond to go somewhere else. Does that make sense? So this bond here went up onto the oxygen, allowing the carbon only to have 4 bonds. So that becomes one of the things you got to look for in organic chemistry. You got to have to watch for that. And these become a big deal in those mechanisms. We talked about those mechanisms last week. Now, let's say we got this molecule. That oxygen there. Now this nitrogen will have a lone pair of electrons. So what we want to do is we want to draw a resonance structure for this. So what happens is you'll notice that this is once again a carbonyl. We've seen 3 carbonyls in a row. So this is a carbonyl. So anytime you see this, this should go, oh, I might do a resonance structure with this carbonyl. You start to kind of see a pattern here. And so you can do that. So now this can go here. So what's happening here now is we had a single bond between the carbonyl carbon and the nitrogen. Now we're going to form a double bond. Now that, if we put the double bond here, this carbon is going to have 5 bonds. So one of those bonding pairs goes up and becomes a lone pair onto the oxygen. Oops. Does that make sense?
Yeah.
Okay. So a lot of this minor, it's just recognition. You're just, oh, you see these carbonyls, oh, I might form a carbon single bond oxygen. It's very common with these. Now, let's say we don't have a carbonyl. Let's look at something else. Let's say we don't have a carbonyl. We have a 5-membered ring. All right. With a methyl group off to that end, a double bond, and then here we have a carbocation. What can happen is now this will be something you'll see further in the future. I don't know if we'll be able to get to it this summer, but this will be something you'll see in the future. This double bond can come over here and move over to here. Now it can do that because this carbon is a carbocation. It's only got 3 bonds with it. Okay? So now, by doing that, we move the carbocation here, and then here is going to be a double bond. Now, what we've done here, once again, I kind of go through these a little bit fast, but I want to go back and talk a little bit about the fundamentals, just some foundational stuff. is we start out with a plus charge on this carbon. So if we were to number these carbons as carbon 1, 2, 3, 4, and 5 on that ring, what we've done, oops, drop this stuff. What we've done is instead of having the plus charge on carbon 2, we've now put the plus charge on carbon 5. In actuality, this plus charge gets delocalized, gets spread out over those two carbons, making it a fairly stable ion. That makes sense?
Yeah.
Okay. All right. Now these can have multiple. See here now. Let's start with something like this, right? And also, there's usually going to be a conservation of charge. If the reactant is going to be positive, then the product has to be positive as well. If the reactant is neutral, the product has to be neutral. So there's usually going to be a conservation of charge. There's always going to be a conservation of charge. So we'll do one more. It's a little bit more difficult, right? These can get fairly lengthy and difficult. This functional group is called an an ester. And what can happen here now is we could take one of these lone pair electrons, right? Oops, what can happen is a double bond can come up to there. It can do that because once again, that oxygen is going to be very electronegative. It's going to want those electrons. That's going to cause that carbon to become a carbocation. Right? What happens? That's a positive, and that's a negative. Okay. Now over here, we've got that pair of electrons, or the two pairs of electrons on the oxygen. Air can come over here, form a double bond. It's going to be a negative charge. This oxygen is now going to be a positive charge. So once again, this molecule is going to be neutral, all right, because we have a positive and a negative as well. And this would be a resin structure that's possible. Not always likely. This would be typically the most stable conformation, but this can happen. This can happen in a way to explain our mechanisms. So far, so good.
Yeah.
Now let's see. Want any more? You kind of get the hang of these.
I think I've got the hang of it.
Okay, they're just because I'm this is a big deal. You have a class in here? We'll do one more. This is a little more difficult. This is a nitrogen one. Now, these you got to be kind of careful with. Well, Dr. Baldwin will talk about that. I'm just kind of getting sort of the basics things of this. All right. We have a molecule such as this. And what can happen is one of these double bonds, one of these bonding pairs can go on to the nitrogen. All right. Okay. And what will form Just such as that. Now this nitrogen will have a negative charge, but now this carbon only has 3 bonds, so that will have a positive charge. So we formed a carbocation. All right. Once again, we go back into equilibrium. And what can happen is that now this double bond can come over to there and form a double bond there to take up that positive charge. Oops. It's still negative, but now that carbon is a carbocation. And what you'll find out, mine is, and those who are going to listen hopefully this later, is that it depends upon which carbon has that carbocation also for stability, all right? Now, the thing about all this is it all has to really deal with electronegativity, and that electronegativity is going to drive you towards thermal stability, some type of energetic stability is how that works. 12 verse 13. Okay, let's see here now. Okay. So those are going to be some examples. All right. Well, we will get to. We'll talk about it just because I want to be thorough. All right. We're done with this stuff. We're done with that stuff. So I'm getting rid of it. Okay, so I can recycle. Okay. I lied. We got more resonance structures. All right. Just because it is a big deal. It's a huge deal. And again, this might be all we're able to talk about today. But at least I want you to see it. So I remember the first time I saw this when I was an undergrad. And that was back in the day. That was a long time ago. And I just kind of shook my head, thought, what in the world am I looking at? Now, what we want to do is we also kind of want to look at some patterns. Right, and hopefully you saw a pattern, at least I pointed out a pattern with the carbonyl. All right, now we want to look at some other ones. Now, we're going to have some vocabulary words. You've taken a lot of biology, minor, and the rest of you folks. So verbiage, as I've said before, if you're going to learn a new science, it's as if you're learning a new foreign language. It really is like that. So the first one is if we're going to look at an allylic pair. All right. So what is an allylic pair? We first want to talk about that. Now, if we have a carbon, double bond to a carbon, and then here we have the methyl groups. The methyl groups. The blue ones that I circle are going to be the allylic. Those four methyl groups are the allylic carbons. Right? They're going to be the allylic carbons. These two carbons, that's not very good. Those two carbons are what are called the vinylic group. So they're going to be the vinylic carbons. Okay. Using this?
No, I was looking for another.
Okay. All right. So far, so good? So one thing you want to do is you want to be able to identify lone electron pairs in the allylic position. And that's spelled. in the allylic position. Okay? All right, so for example, we have another example, we can look at this. And we've already seen this one, or one similar to it. All right, so here are going to be the vanillic carbons. This is going to be the allylic carbon. We have a lone pair on the allylic carbon. What can happen is this can form this lone pair can form a bond, a double bond here. That can go right there. So what we've done is we've turned this vanillic carbon into an allylic carbon. By moving this and forming a double bond, what was once an allylic carbon can become a vanillic carbon. This becomes such as that. That would be a negative, and that would be a negative 12. All right. I should have put a allylic pair of electrons. Give me a second, mine. I got my daughter here. She's supposed to go hang out with a friend. So I'll just pause this real quick and I'll be there. We go. All right. Let's see now. So the second one, once again, we're going to look at the allylic. But we're going to look at a positive charge. We're going to look at this positive charge. Now, the nice thing about that book I suggested, it starts out with small molecules and it allows you to build it to more complex molecules. And that's kind of a nice thing. I always think organic chemistry, we should be starting out with smaller molecules. And Mina, you're a biochem major, is that correct?
Yeah.
Okay. What you're going to notice as you go through chemistry is when you took chemistry with me, we looked at small molecules. We didn't look at very big molecules. When you go to organic chemistry, the molecules start to get bigger and more grandiose. When you go to biochemistry, they get to be huge. Okay? So that's sort of something to kind of know. So hopefully if you happen to purchase that book, great. The author that will start with very small molecules, which is kind of nice. So what we want to do here now is we're going to look at how the positive charge, once again, still under resonance structures, how the positive charge moves to the allylic positions. Okay? So if we've got a molecule such as this, now this one we have a positive position. So here's going to be an allylic position. This is going to be a vanillic, 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 allylic. Does that make sense? And what we're going to do is we're going to take this double bond, move it to there, right? If we do that, right, we've got the double bond here. That's going to make this a positive charge, all right? This is still going to have a double bond here. So what we have is we have a vanillic, vanillic, allylic, vanillic, vanillic, allylic. Okay? Now we can keep doing this. We can make another resonance structure such that this double bond goes there. And we end up getting. And that puts the positive charge right there. Okay? So we have a vanillic, 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 allylic, allylic. All right. So these are just simply patterns, just patterns that you can recognize for when you're looking at resonance structures. That's number 2. And we have number 3. We're looking at now lone pairs. Adjacent to a positive charge. Right. Now, negative charge there. What can happen here? Well, it becomes kind of obvious. You have something negative and something positive. That if this donates a pair of a lone pair of electrons, it becomes a bonding pair. Then what we end up getting is a structure such as that. Okay. So far, so good?
Yeah.
Okay, now I'm gonna trick you, okay? All right? Just be prepared. And this is that subtlety of science. It's just, particularly in any one of these branches, you can be tricked, and that's certainly not my intention here. I want you to see some things, but I want you to be out to recognize it. You can easily be tricked into something, all right? You have a nitrogen double bonded to an oxygen. This can be bonded to a methyl group. And over here, you have something like this, okay? Now, what we've got now is we've got this oxygen, which is negatively charged, bonded to a nitrogen, which is positively charged. And what you would want to do is you'd want to move one of these pairs of electrons right there. Now, the problem that cannot, and the result of that, I'm getting ahead of myself, the result of that is that you have a nitrogen now with 5 bonds or 10 electrons. So you can't do that, right? It doesn't work out this way. So this cannot happen. It's wrong color. I want to use red. This cannot happen. It's not going to happen like that, okay? That's not going to be the first step, all right? This is where it becomes, like I said, a little tricky and a little, I don't know, nitpicky, I guess. So let's look at this again. Let's look at how we can do this. How can we draw a resonance structure for that molecule? So we have a nitrogen, methyl, oxygen, oxygen, negatively charged, positively charged. What happens here, what has to happen here, number one, is that this pair of electrons has got to go up there. So that becomes your number 1 step, right? That's your number 1 step. All right. What we have is a nitrogen, move on to an oxygen, negative, that, oxygen, negative. Okay, that's what we've got. And what happens now is that this pair, one of those lone pairs from that oxygen, goes and forms a double bond with the nitrogen. And we get a nitrogen, negative, negative. Oop, I gotta have myself. There's no negative there. There's actually a double bond and it becomes a positive. And now this, it's a negative charge. This is now valid because we've not violated the octet rule. So far, so good?
Yeah.
Okay. A little confusing.
Slightly more than everything else.
Yeah,
but-
this is kind of where the confusion comes up because this is new. We've not seen this before. So watch some videos on, I can't, watch some videos on resonance structures because it does become a big deal. And if you have questions, let me know. I'm taking my time over this because it is a big deal. It is such a big deal for this branch of science. It's a huge deal. All right. Here. Look at another one. So number 4. So if we have a pi bond, remember a pi bond is going to be a double bond, right? Between, oops, I can spell, not really. Between two atoms of differing electronegativity. Remember? There's that electronegativity. So to really be good at organic chemistry, electronegativity's gotta pop in your head all the time. It's always gotta be there. And then, if we have, I don't know if we have time today, but the next one will wanna be acid-base chemistry, right? So in this case, we've seen this molecule before, we've seen this before, right? But because of the difference in electronegativity, right? Here we have our pi bond, here we have a difference in electronegativity. The most electronegative element on the periodic table is fluorine. The second most electronegative element is gonna be that oxygen. So this is gonna take, and this is, once again, this is going to be a carbonyl. We'll go over function groups. I don't know if we'll do function groups for acid bases. I'm not really sure. We might just do acids and bases, and then do function groups. But this is a function group you'll want to know and keep your eye out for a minor, and the rest you, because you know how to deal with carbonyls now, hopefully at this point. Right? And this, oops. Now, does that make sense?
Yeah.
Okay, and you'll see this one a lot. Not only just with carbonyls, but you see it with halides. You'll see this a lot, all right? I'll give you a little heads up. Alkyl halides. Keep that in the forefront of your mind, because that becomes a big deal too. I know I'm saying it's a big deal, it's just you'll start to hopefully see a pattern through all of this. You'll see that, except that won't have pi bond, All right. Last and not least, number 5. Conjugate pi bonds in a ring. So it'll be in a ring. So for example, if we have benzene such as that, what can happen is that can go there, that can go there, that can go there, and what you see now is double bond there, now double bond there. And this can actually be drawn, you'll see this drawn now, like that. That's the same, because you have that resonance structure. How are we doing? So far, so good?
Yeah.
Okay. Now that we've done this, did you happen to pick up that book, that Smith book?
Yeah.
You did, okay, all right. So I'm kind of going right along with that. I took my notes right from it. I stole it right from it. It's just a nice resource. So if we look at the significance, of resonance structures, all right? What is the significance of this? Why are these such a big deal? Well, one thing I mentioned is you want to minimize charge. You want to minimize charge. The most stable of all the compounds is the one that doesn't have charge. Okay? So if we look at you know this molecule we talked about in inorganic chemistry, but this is acetic acid. Right? All right. We can draw this as such. It's possible. Oops, here, we'll do it this way, sorry. A pair goes there. A lone pair goes to form this carbon with this carbon. One of the double bonds of the carbonyl goes up to the oxygen. We have a double bond here, this becomes positive, and that becomes negative. Now this is possible. Not real likely, but it's possible, all right? All right. And then once you get into thinking about these stabilities, mine and the rest of you, we're gonna look at acid, and then that becomes a big deal too. So we can look at the acetate anion. Look at the acetate anion. Now this is why this is so stable. So we now have a negative charge on this oxygen. A lone pair can go there, causing one of the double bonds to kick up there. Hopefully you start to see a pattern with these carbonyls. And all we've simply done now is we move the negative charge from this oxygen to that oxygen. In essence, we've taken that negative charge and we've distributed among two atoms. Now, as you know, one thing, the reason my dad hated chemistry because of exception. And simply due to time, I'll let you folks read on them, okay? I've only got the summer, and that's it. If I was teaching a 16-week course, we would talk about this quite a bit, but there are quite a few notable exceptions for this. One of them is pyridine. That's kind of interesting because that has to deal with that deals with geometry, and so that's really kind of a neat one. But that's a really big exception. All right, let's see here now. I'm trying to figure out which way to go with this. Doesn't really matter. All right, we're going to talk about some stuff that we've talked about before. We got what, 15-ish minutes, and I got a meeting today. All right. So we're going to talk about a little bit about acids and bases, and I'm going to just kind of give you the acid. We're going to just kind of do the abbreviated version of this, okay? Now, in this case, when we talk about acids and bases, in equilibrium, right? We get some acids and bases in equilibrium, okay? If we have an acid in water, it's going to dissociate as such, right? This should bring back hopefully good memories, maybe some bad memories from last semester, but we talked about this quite a bit. Where the equilibrium constant is going to be equal to the concentration of the acid, conjugate acid, times the concentration of the conjugate base, divided by the concentration of our starting acid. All right. If we have a large K, if we happen to have a large K, then that means that the products are favored. If we have a small K, That means that the reactants are favored. Okay? Now we can tie this in with pH, right? So we can tie this in with pH. Remember, pH is the minus log of the concentration of the acidic, of the concentration of the acid. And it's going to be this acid, the one that's dissociated, right? Basically the conjugate base or the conjugate acid. If we have a pH between 0 and 7, we know this is going to be acidic. If we have a pH 7 and greater, we know that's going to be basic. The actual range, the real range is really a negative 1.1 to 15 is really the range. Okay. All right. Now, we've looked at those Ks, right? So we know that a Ka is going to be the equilibrium constant for an acid. And this is basically, a lot of this is going to be a review, okay? And what we can do now is we can take the pKa. So we look at the pKa, which is equal to the minus log of the Ka. Now, if we have a low pKa, we have a strong acid. And what that means, now I talked about this in the spring, but I don't expect you to remember, and that's perfectly fine. If it has a low pK, it's going to be a strong acid. This is a not stable acid. Meaning it wants to dissociate. It wants to break apart. Okay? If we have a high pKa, this is a weak acid. And what that means is that it is a stable acid. In essence, another way we can write this is that this not stable acid, this is reactive. And this is not as reactive. Does that make sense?
Yeah.
Another way we can write this, certainly we're talking about the high pKa, okay? Because those are the ones we're going to see. We can say that this is less acidic or more basic. Right. Now, we didn't spend much time talking about pKa's at all, but Dr. Baldwin will, okay? And now, as I said, in organic chemistry, there's two things you want to keep in the back of your mind, and it just helps you, at least if you're a Y person. You want to keep that electronegativity, and you want to keep the acid and base. If you keep the acid and base, you got to include these pKa's. You got to have a good intuition as to how these pKa's work. All right, in the sense that if you have a low pK, that's going to be a strong acid. If you have a weak pKa, that's going to be a weaker acid. All right, you kind of want to just get used to that. you want to put some meaning to those numbers. And that's my goal. I'm going to try to put some meaning to these numbers. That's what I'm hoping to do. All right? All right. So just help build with the intuition, all right? If we happen to have pK of an acid is 5, and the pKa of another acid is 10. Oops, sorry, not 10. Oh my goodness. Get ahead of myself. 15. 15. Okay? What this says, what this indicates to us is that this acid you ready for this? Is 1 times 10 to the 10th times stronger. Of an acid. And recall, does that make sense? Because this is on the log scale. It's on the log scale. Okay. And then strong acids dissociate into weak conjugate bases, and weak acids dissociate into strong conjugate bases. And things that are weak are very stable. And remember, nature wants to work in such a way that it moves to stability, because when we say it's very stable, we're saying it's lower in energy. It's lower energy. All right. All right, how's that, bud? Is that good?
Yeah.
All right. I got a meeting a little bit. Let's see here. I think next week we'll go back to Thursday. I might even do one on Tuesday for those of you. I might do one Tuesday and Thursday of next week. Just so we can kind of get a bunch of this stuff knocked out and actually get to the organic chemistry. So if that's the case, I'll just send out some Zoom links. And it'll be 7:45 either Tuesday, it'll be definitely for Thursday. And if I don't go fishing on Tuesday, we'll do one on Tuesday as well. Tuesday at 7:45, because Zahir wants to 7:45 works for her. So
Okay.
all right. Is this helping? Well, you won't know till you get into the class, right? Once you get into the class.
Yeah.
Yeah.